Hello, everyone. In this class, we want to look at escape velocity. Escape velocity. Escape velocity is defined as the minimum velocity required for an object to escape from the gravitational field of a planet completely. In my earlier video, we looked at acceleration due to gravity, gravitational field, gravitational potential and potential energy, Newton's law of universal gravitation, and gravitational field strength. So I advise you get that video so that you get more information about what we are looking at here. So we have defined the escape velocity. There is the minimum velocity required for an object to escape from the gravitational field completely of a planet. So, as we all know, any object within a gravitational field will be attracted by gravitational force. So that minimum velocity that will be given to an object required for an object to escape from the influence of gravitational field of a planet completely, we call it escape velocity. So in launching of a rocket and spacecraft, we need to give the rocket that minimum velocity for it to escape from the influence of gravitational field. Assuming this planet Earth, we want to launch a rocket from the surface of the Earth. That minimum velocity that must be given to it for it to what? Escape from the influence of the Earth's gravitational field is what we call escape velocity. So we can calculate the escape velocity from principle of conservation of energy. The energy can neither be created nor destroyed, but it can change from one form to another. So let's see how we can calculate escape velocity for rocket, for spacecraft, or for any object we want to launch into space, how we can calculate the escape velocity. So if we have a rocket with initial velocity, a rocket with initial kinetic energy, and we want to launch it into space. The total initial energy of the rocket is given by the kinetic energy, let's say initial, plus the gravitational potential energy, the initial value. Let's call this equation 1. From here, if we substitute, we will have the initial kinetic energy, the gravitational potential energy. And gravitational potential energy of a planet is given by this expression. So let's call this equation 2. We want to launch the rocket like we said. First of all, we need to get the total initial energy. Then we will now get the total final energy. So from the total initial energy, we say the energy of the rocket will be the kinetic energy and the potential energy. And the potential energy we are talking about here is gravitational potential energy, which is given by this expression. G here is the universal gravitational constant. M here is the mass of the planet. mass of the rocket to be launched, then r is the distance from the center of mass of the planet to the center of mass of the rocket. So, if the rocket managed to escape the gravitational field of the planet, then we can have that the gravitational potential energy will be equal to 0 at that distance. And if we assume that the rocket has no potential, no kinetic energy at r equal to infinity, then we can have that the total energy final will be equal to kinetic energy final plus potential energy final. And from this assumption that when the rocket is being launched at a distance at infinity, it has no potential energy. And the kinetic energy at infinity, there is no kinetic energy at infinity. Then we can have that the total energy when it is being launched is equal to final kinetic energy plus final potential energy. So from here, we can have that by principle of conservation of energy, the total initial energy is equal to total final energy. So the total initial energy given by equation 2, the total final energy is given by equation 3. So if we equate them, we will have that we will have this expression, the kinetic energy total initial plus minus will be equal to 0. So we'll have the total initial energy equal to total final energy. And this is the total initial energy. So it is equal to this. The total final energy is equal to 0. So we have to equate. So we can simplify this now. Let's simplify and see. So if we simplify, kinetic energy is half mass of the rocket velocity will be equal to, as we cross this to the equality sign, this negative, we turn to positive. G, mass of the planet, mass of the rocket over R. So if this cancel this, we'll be left with what? Half V escape over G mass of planet over R. So if we simplify this, we'll have cross multiply 2G mass of planet over R. So we use this expression to calculate escape velocity. And we say escape velocity is the minimum velocity required by an object to escape the influence of gravitational field. So but G, which is gravitational field strength, I earlier advised that you look at my earlier video on gravitational field strength, which is given by this expression. From here, if we cross multiply, have gr squared over gm planet. So in place of gm planet, we can simplify, you can substitute this. And if we do that, so if we call this equation 3, okay, this equation 3, this equation 4. So put equation 4 in 3 for gm planet. So if we do that, escape velocity can also be written as, we substitute in place of this, we are putting this. So you have 2gr squared over r. So if we simplify, we will have 2gr. So this is another expression that we can use to calculate the escape velocity. So here, we can compute escape velocity of a planet if we know the gravitational constant, we know the mass of the planet, and also the distance of the object from the surface of the Earth. We can also calculate if we know the gravitation acceleration due to gravity of the object. So these are the two formulas that we can use to calculate. And if the planet we are considering, assuming is Earth, the escape velocity now can be written as 2gr, where this r is the radius of the Earth. So depending on whatever we are looking at. So these are the two formulas that we can use to calculate escape velocity. Okay, let's solve some example to really understand what we are talking about. Example: a rocket blasts off from the surface of the Earth. Calculate its escape velocity. If the same rocket were to be launched from a space station located 50,000 kilometers from the surface of the Earth, calculate its escape velocity. Solution: by principle of conservation of energy, for the rocket to escape from the gravitational field of the Earth, it means the kinetic energy plus the potential energy must be equal to 0. By that, we said kinetic energy So this is the expression we shall be using. The kinetic energy is equal to this. The potential energy is given by this expression. So mass of the Earth, in this case, the planet we are looking at is the Earth. Mass of the rocket. Then since the rocket is being launched from the surface of the Earth, we are using radius of the Earth. Okay, let's simplify and see. From here, the escape velocity v will be equal to 2 So let's simplify and see. The escape velocity will be equal to Okay, so from here, we have simplified, making escape velocity to be a subject of formula. So if we substitute to this universal gravitational constant, mass of the Earth, then times mass of the Earth Okay, this one is not there. So from here, we have gotten the escape velocity to be this. Then the next question says, if the rocket were to be launched from 50,000 kilometers above the Earth's surface, the distance r from the center of mass of the Earth to that of the rocket, r, the distance, will be equal to the height plus the radius of the Earth. So that will be, the height is 50,000 kilometers. The radius of the Earth, 6.4, 10 to power 6. So we try to convert everything to meter. So let's substitute and see. V escape will be equal to 2g mass of the Earth So if you simplify, 2 times 6.0 So if you simplify that, you will have 3.8 times 10 raised to power 3 meter per second. So this is what we are saying. Initially, the rocket is launched from the surface of the Earth. We computed the escape velocity to be this. And later on, it is to be launched from a height of 50,000 kilometers. So we convert the kilometer to meter, then the radius of the Earth. So from here, we simplify 2 times universal gravitational constant, giving us this, the mass of the Earth, and this distance. We simplify this, we will have 5.6410 to power. So this is how we substitute, and this is the answer, the escape velocity. I hope it's not difficult. So all we need to know remember the formula. Is it launched from the surface of the Earth? You simplify. If it is launched from a given height, then you need to add the height to the radius of the Earth. And from there, we simplify and we get the escape velocity. Is that taken? Okay, let's make progress. The next thing we want to do, we want to look at Kepler's law. Let's look at Kepler's law of planetary motion. As we know, say the solar system consists of the sun and the 8 planets that revolve around it. So the planets revolve around the sun in elliptical or near elliptical orbit. So with Kepler's law, we can get information about the motion of planetary bodies around the sun. So we have 3 laws, Kepler's law, the first one, second, and the third. For an object, planetary bodies moving around the sun in elliptical or near elliptical orbit. So Kepler's first law states that the orbit of a planet is an ellipse with the sun at one focus of the ellipse. So we have earlier said that if we have the sun, each planet revolves around the sun in an elliptical orbit. And at each point, the sun is always at a focus. So according to Kepler's first law, that the orbit of a planet is an ellipse with the sun at one focus of the ellipse. So as the planet moves around the sun, at each point in time, the sun is at a focus. So this is Kepler's first law of planetary motion. Let's look at the second law. Kepler's second law. Kepler's second law states that an imaginary line drawn from the center of a planet to that of the sun sweeps out equal areas in equal interval of time. Let me explain here. You have the sun, and each planet revolves around the sun. And because of the elliptical nature of the sun, if we draw an imaginary line, at a point, the motion of the planet is faster. Let's say faster motion. At another point, maybe a slower motion. Faster motion, slower motion. But irrespective of how the motion is, equal areas is covered in equal interval of time. So that is Kepler's second law of planetary motion, that each object moves in an elliptical orbit around the sun, and that the movement is not uniform. At times, there may be a faster motion, at another point, slower motion. But irrespective of the nature of the motion, the equal areas is covered in equal interval of time. So that is the statement of Kepler's second law, that if we draw an imaginary line from the center of a planet, so if we take a planet to be at this point, to that of the sun, that it sweeps out equal areas in equal interval of time. So this is Kepler's second law. Let's look at the third law. Kepler's third law. Kepler's third law states that the square of the orbital period of a planet is directly proportional to the cube of the semi-major axis of each orbit. Let me explain that. That the square of the period of a planet is directly proportional to the cube of the semi-major axis of each orbit. So this is the third, Kepler's third law of planetary motion. Let's derive how we arrive at this so that we can better understand the expression, also use it to solve problem. So if we consider the motion of a planet, we have the sun, have a planet, and the planet is being attracted by gravitational force. So as the planet moves around the sun in an elliptical orbit, if we take this to be the major axis and the distance r, as the planet moves around the sun in a circular path, it has centripetal force. It is attracted by centripetal force. And the centripetal force is equal to the gravitational force. And centripetal force is given by this expression: mass of the planet, the distance, angular frequency is equal to gravitational force from Newton's law of universal gravitation. We have that we have this expression from Newton's law of universal gravitation. So from here, we can simplify. But omega is equal to 2 pi over t. If we remember, period is equal to 2 over omega from circular motion. So in place of omega here, we can substitute this. So if we do that, we will have this expression mass of the planet can cancel mass of the planet. So we will be left with what? 2 pi, let's open the bracket, 2 pi square t equal to g So from here, we open the bracket, so let's make t the subject formula. We simplify, we have t squared will be equal to 4 pi squared over So through this, we have derived the expression for Newton's third law. And all we did is that if you have a planet revolving around the sun, that the planet is attracted towards the sun through a gravitational force from Newton's third law. And as the planet is moving in a circular path, it moves with centripetal force. So we are saying that the centripetal force is equal to the gravitational force. This is the expression for centripetal force. I advise you watch my video on circular motion so that you understand more about centripetal force, centripetal acceleration. Are we together? So from here, if we substitute centripetal force given by this expression, gravitational force from Newton's law of universal gravitation, that the force of attraction between two masses, the sun, the planet, is given by this expression. Then we have established that angular frequency is related to the period by this expression. So in place of angular frequency here, we can substitute this square, and if we simplify, the mass of the planet will strike out. So from here, if we cross multiply this by this, we will have this. Are you following? Okay, from here we are want to establish relationship between T and R. So if we simplify, opening the bracket, squaring both sides, from there we'll have this expression. And if we go further, we will have this. So from Kepler's third law, what does the law state? That the square of the orbital period is directly proportional to the cube of the major axis of each orbit. So that the square is directly proportional to the cube. So if we remove this, put constant of proportionality, which is all this, then we'll have r to power 3. So this is the constant of proportionality. So with this, we have proved that Kepler's third law, the square of the period is directly proportional to the cube of the semi-major axis of each orbit. So we have proved the statement of Kepler's third law. Okay, so we have derived the Kepler's third law of planetary motion, which is given by this. I hope you understand this derivation, how we come about it. Okay, thank you very much. Let's look at an example of how we can use all that we have looked at. An example. A satellite of mass 2,400 kilograms is placed in an orbit at a distance of 4.23 times 10 to the power 7 meter from the center of the Earth. Calculate the angular velocity or angular frequency of the satellite, the period of the satellite orbit, the speed of the satellite, acceleration of the satellite, and force of attraction between the Earth and the satellite. Solution. From the equation, we have the Earth, then we have a satellite which revolve around the Earth, and the distance from the Earth to the satellite is 4.23 times 10 to power 7 meter. So the first question says we should calculate the angular velocity. For this satellite to move around, we say that centripetal force will be equal to the gravitational force. And from here, we will have mass of the satellite, the distance, angular frequency will be given by so from here, this and this will go. And we'll have this to be equal to I hope you are following. Okay, let's simplify and let's substitute and see. Gravitational constant, mass of the Earth. So if we simplify this, we'll have the angular velocity to be so that is our angular velocity. The second question says we should find the period. Using this expression from here, period will be equal to 2 pi over omega. So let's substitute. If we simplify, we will have this. That is the period. So by this, the satellite takes this to what? To make one orbit, one complete oscillation. The next question says we should find the velocity of the satellite. And from the relationship between angular velocity and linear velocity given by this expression, if we substitute, we will have this and if we simplify, we will have this expression. Okay, the other question says we should find the acceleration. And acceleration is given by this expression. So if we substitute, okay, then the last one says we should find the gravitational, the attraction. So from here, we can have that the gravitational attraction is equal to the centripetal force, which is equal to mass of satellite so if we substitute, okay, so we are saying that try to use the Kepler's law that we just derived to solve a problem. That if we have a satellite revolving around the sun in an elliptical orbit, revolving around the Earth, and the distance between the Earth and the satellite is 4.23 times 10 raised to power 7 meter. The question says, as the satellite is revolving, it has a centripetal force that keeps it, which is attracted towards the center of the Earth. And the satellite is equally attracted towards the Earth by a gravitational force from Newton's law of universal gravitation. So we can have that the centripetal force is equal to the force of gravity, the gravitational force. So centripetal force is given by this expression, and from Newton's law of universal gravitation, we have this expression. So the mass of the satellite, we cancel that out since it's common on both sides. Then we are looking for, we cross multiply. To this side, we have this. Then we are looking for angular velocity, not the square. So we square both sides, we have this. So as we substitute and simplify, we have the angular velocity of the satellite as it is moving in a circular orbit around the sun to be given by this. I hope that is clear. Okay, the next thing we have to find the period. What is period? The time taken for an object to complete one oscillation. So as the satellite revolves around the Earth, what time will it take to complete one oscillation? The time taken. So using this expression, I believe you are familiar with this expression. From there, we make the period subject formula. And when we substitute, we have this as what? The period that the satellite will take to complete one revolution. Then the next question says we should find the velocity. And this is the expression that relates linear velocity to angular velocity. Already we have gotten the angular velocity to be this. Then the distance, this is the distance. So if we substitute, we have this. Is that taken? Then the next question says we should find the acceleration. And this is the expression we are using. Already we have computed the velocity to be this, square of it. Then the distance is the same as this. We substitute, simplify, and we have this as the velocity. Then the last one says we should find the force of attraction. And from here, we say that the gravitational force is equal to the centripetal force. So, given by this expression. So we know the mass of the satellite. It was given in the equation 2,400 kilograms. We have computed the velocity. So we substitute, sorry, is the square of it. We substitute the distance given by this. Simplify. So the force of attraction here, Fg, which is equal to Fc, is 538 Newton. 538 Newton is the force of attraction. So I hope you understand. So this is how we go about using Newton's law of Kepler's law, as well as Newton's law as well as a object moving in a circular path, the centripetal force. So thank you very much for watching. Please like, share, and subscribe to my channel for more interesting videos.